Hello, everyone, and welcome to the Department of Energy's SBIR STTR FY25 Phase 1 Release 1 Topics webinar. My name is Zina Al-Yusuf. I am with the DOE SBIR Programs Office, and I will moderate today's webinar and provide you with some basic topic information as it relates to Release 1. Following the introduction, this introduction, you will hear from the topic managers that oversee topics 23 through 33 as they clarify their expectation and answer some questions that you may have regarding their respective subtopic. During this webinar, you may submit topics-related questions via the Q&A box located at the bottom of your screen. We will group these questions and submit to the managers following each topic presentation. Please remember, and this is very important, remember to include the topic and subtopic number with your question. That will help us keep track of questions submitted. If you have a funding opportunity announcement or other non-topic related questions, please save these questions for the Phase 1 Release 1 Funding Opportunity Announcement webinar. Webinars actually scheduled for Thursday and Friday. So for Thursday, August 8 and the Q&A on Friday, August 9, and we'll explain that in a minute. Finally, a copy of the presentation and the recording of the webinar will be posted on DOE SBIR STTR website under the Funding Opportunities webpage. The topics, the program represented today are Office of High Energy Physics, topics 23 through 29. Office of Nuclear Physics, topics 30 through 33. This is the third and last webinar in a set of 3 webinars for Release 1. And today we will cover the two programs we mentioned. The programs participating in this release are 6 programs, and we have about 95 subtopics. As you can see, the topics document was issued on July 8, and this week we are hosting the topics webinars. The funding opportunity is usually released about 3 to 4 weeks after the topics are issued. We do this to give you enough time to read through the topics document and ask questions so you can make up a more informed decision as to whether or not you might have something that is responsive to what we are looking for in this release. The most important date following the opening of the funding opportunity is the letter of intent due date, which is the first step you need to take in order to submit a full application. DOE is the only federal agency that requires a letter of intent. It tells us who you are, what topic, subtopic you are interested in applying for, and a little bit about why you think you are responsive for that topic. So basically, if you do not submit that letter of intent, then you cannot submit a full application to the funding opportunity announcement. As mentioned, we have 6 programs participating in this release. We have covered topic 1 through 11 and 12 through 22 in the 2 topic webinars that we hosted on July 23rd and 24. And today we'll wrap up with the topics from the 2 programs we mentioned earlier. The funding opportunity is scheduled to be issued on August 5th. After that, we will have the funding opportunity webinars. This year, we are doing something different than what we did previously. We will have two webinars for the FOA. The first one on Thursday, August 8th, and that one is dedicated for the overview of the application process. So it's only the presentation. And the second webinar on Friday, August 9, this webinar is dedicated for the Q&A, to answer questions. We do this to give you the time, to listen to the process and read about it, and then join us the following day with your questions. Both recordings will be posted on our website under the Funding Opportunities webpage. However, today we are going to discuss the topics in a little more insight than what is provided in the topic document. Please remember to join our mailing list if you haven't done so already. So you can receive a notification from us when topics are released, webinar registrations, and some good information applicable to each cycle as we move through the phase 1 process. Also, I would like to mention that we use GovDelivery, a news application platform, to send emails and notifications. Please work with your IT group to allow you to receive these emails. DOE Phase 0 Assistant Program is now open to all first-time DOE applicants. So if you have never applied to DOE before and looking for application assistant, I encourage you to go online. You can find the link here or go to our website under Applicant Resources page and click on the link. That will take you to the Phase 0 website, where you can complete a 3-minute application to see whether or not you are qualified for that service. It is a first-come, first-serve service, but it is something that can help you go through the application process. Just to give you a clear picture about our topics here, they are created by DOE program managers and define important technology breakthrough needed in the R&D areas that support the DOE mission. The topics are written in a way that support the topic managers' role in their offices. Many of these topics are related to the topics that they are sponsoring in one of their universities or national labs. When you go through the topics document, you'll see that the topics are arranged by program offices and organized alphabetically and numerically, and that is the way we are going to refer to them. What we ask you to do first is read the topic and subtopic and the reference information that is provided to get a little more context as to what the topic managers are looking for. When you contact the topic managers, it is for clarification purposes. We are not asking them to tell you whether or not it is a fit for what they are looking for. The feedback they give you is to help you determine whether or not your innovation would fit what they are looking for. Regardless of what you might hear from the topic managers, the decision to apply is yours. Here we have an example of what a topic looked like. We always have a topic header, that is the blue banner you see below the topic title and above the description. And it gives you important information like if the topic accepts STTR, yes or no, and the maximum award amount for that topic. Not all topics have the same information. They vary by program and by topic as well. So please pay attention to such information. The general topic description explain what the topic is about and maybe some context on where it falls within the mission of the program. Below that, you see subtopics that describe specific opportunities in which proposals are requested. You will notice that a good number of the topic have a subtopic titled as Other. Under this subtopic, you can submit proposals that fall within the general topic description, but do not fit with any other subtopics. After each subtopic, there is question dash contact, then the name and email address of the point of contact that you can reach out to with your questions. Please note that every SBIR or STTR application must include the topic and subtopic number to which you are applying for. So please remember to include the topic and subtopic in your application. That is just a brief review, overview, and now we will start with the first topic in today's webinar, and it's topic 23. Craig, are you online?
I am.
Go ahead, please.
Okay, and you don't want us to read the topic, but just provide some high-level comments on it.
Yes, please.
Yes. Okay, so there are 3 subtopics on this topic. The first, topic A, graphical user interfaces for accelerator modeling. What we're looking for are significant advancements in modeling beam physics and the design of accelerators and beamlines, more advanced simulation codes for specific beam physics and accelerator components. Another point of emphasis, more intuitive user interface, such as user-friendly GUIs, which not only help to understand the simulations results, but also enhance modeling efficiency and facilitation of benchmarking of simulation results from different codes and experiments. And lastly, end-to-end simulations by transporting and integrating simulation results between codes and suites of codes. Subtopic B, digital twins for HEP accelerator beam test facilities. We're looking for, and of course this is an aspirational goal, creation of a digital twin of a DOE accelerator test facility, and steps towards that, which would allow for the exploration of machine tuning, AI/ML controls and development to enhance new experiments. And then the third subtopic, non-destructive electron beam position monitors, looking for non-destructive BPMs, which are needed for the very short duration electron beams in plasma wake field accelerators. The bunch lengths of these can be as short as 10 femtoseconds in a very strong electromagnetic background environment. And so we're asking for quantum improvements in cavity BPMs and advanced BPM concepts. Hopefully that will be of use.
Okay, let's see if there are any questions. Okay, it's not related to the topic. If a person is asking how to join the mailing list, please send me an email and I'll walk you through. I'll type my email address in the answer and send it to you. I don't see any questions for topic 23. Let's wait another minute and see. Just to give people the chance to type and submit their questions. Otherwise, we'll move to the following topic. Okay, for subtopic C, are you looking for sensors?
Yes, yes. Preferably non-invasive sensors, such as a beam position monitor. The issue is our traditional beam position monitors simply don't have the sensitivity and resolution to resolve the fine details of these 10-ish femtosecond duration beams. So yes, so the answer is yes, but in a new paradigm of dimensional space.
How complete does the DT need to be?
DT.
Yeah, that's for subtopic B.
Oh.
Or okay, so how complete does the DT need to be? Or can the DT be a plan or framework which would work for a DOE facility?
Clearly, given the current state of technological development, a digital twin that provides a complete high fidelity simulation of a complete accelerator facility is a tall order. But we would want a usable tool. It may not capture all physics, but it should target some aspects of the physics that would be useful and provide a development pathway to a tool that would be more broadly applicable. I think something that is just bits and pieces but does not deliver a tool would fall short of our expectations.
Thank you. No more questions, so we can move to the next topic. Oh, it is, and here's another question for 23B. Digital twins implies modeling physical presence into the 3D modeling in VR/AR display. What is the physical presence that needs to be modeled and its size?
We're looking for a digital twin, as stated very clearly in the call, a digital twin of an existing DOE accelerator test facility. There's a number of those. We won't go into those in today's thing. If you have further questions on this, please email Darren Lee, the program manager for this topic. But ultimately, the successful applicant will be engaged with a national laboratory where one of these test facilities exists and be intimately familiar with what the capabilities and scope of these facilities are. This cannot be done in a vacuum.
Thank you. So we'll go to the next topic. '24. And it's also you, Greg. Go ahead.
Okay, yeah, so we've got 24. 24 also has multiple subtopics, and I'm going to have to go through a few screens here to get all this to you. So the first subtopic, A, is for low-cost radio frequency power sources for accelerator applications. The aim of this topic is to advance the state-of-the-art in efficiency and cost of RF power amplifiers. There's 5 principal types of sources are defined in the call, each with different frequencies, power and duty factors. Applications must focus on one of these types. The metrics for success are defined for each type. Pay particularly attention to the metrics marked with an asterisk, as these are target values your application must meet or exceed even if other listed metrics are only approximately met. And there are extensive references provided at the end of the topic to describe the applications motivating each type of source. Let me move on then. Let's get through all these and we can take topics after the end. So subtopic B, new tunable superconducting cavities for proton accelerators. Existing cavity tuners are based on ferrites, ferroelectric or piezoelectric materials, and in general limited by a narrow tuning range and high power loss. This topic is aimed at new cavity designs that include the capability to tune over a broad range while preserving high performance, including high Q, high gradient, and high beam power. Primary R&D partners are SRF groups at Fermilab and Jefferson Lab. Third subtopic, C, auxiliary components and instrumentation for superconducting RF cavities. There's a strong push to higher performance SRF cavities that requires commensurate advances in auxiliary systems, and that's the focus of this topic. The need is for higher power capacity often means very expensive auxiliary components, so a key metric is cost-effective components, such as those listed in the topic language that are capable of sustaining higher powers, higher gradients, at higher Q factors than current state-of-the-art. Very helpful resource is reference 2 in the topic language. It provides the current HEP roadmap for RF R&D in the US, including SRF. Okay, I think that's the range of subtopics, so I'll pause at this point.
Okay, I don't see any questions submitted. Okay, here's a question. Are you looking for better characterization of HTC surfaces, a tool more sensitive to Q reduction impurities?
That is not directly addressed in the current solicitation. If you want to pursue that further, I would suggest emailing Ken Markin, who is the primary program manager for the SRF subtopic.
Thank you. I don't see any questions, so we can move to the next topic, 25.
Okay, let me get a drink of water first.
Go ahead.
Okay. 25 is laser technology R&D for accelerators. We have really one subtopic, which is aperture scaling, high performance diffraction gratings. Let me just say first that the aim of this topic overall is to develop suppliers of ultra short laser components, pulse laser components. And the focus in 25 is on high efficiency, large aperture diffraction gratings for high energy, i.e. greater than a joule lasers. Subtopic A, aperture scalable high performance diffraction gratings. Applications must focus on grating fabrication techniques that, one, can be scaled up to large apertures, here defined as greater than 10 centimeters by 10 centimeters. 2, yield very high efficiency, broad bandwidth, high uniformity, high damage threshold gratings. And 3, are appropriate for use with near IR, 0.8 to 1 micron, or LWIR, 10 micrometer gratings. And please read the subtopic carefully for additional requirements and details. Then there is an other, and I'll just say on that, to be responsive, applications must clearly describe how they will enable performance parameters for one or more of the three types of lasers outlined in the table on page 60. Well, I don't know if it's still page 64 or not, of the topics. Applicants are encouraged to read the Laser Technology Workshop Report, which is found as reference 1 in the topic verbiage. And so I'll pause at this point.
I don't see any questions, so we'll move to the next topic. 26. And it's also you, Craig.
Oh, yes, it is. Hang on, let me find my notes here. Oh. Here we go. Oh. Yeah, so high temperature superconducting magnet technology. The motivation here is to push the highest possible magnetic fields. And of course, there are synergistic applications in other areas. We have two subtopics here. A is high temperature superconducting wire and cable technologies for magnets. The aim of this subtopic is to push wire and cable technologies to higher performance and lower cost. This is not an ask for basic material science, but rather the technological development for real superconducting magnet conductors. So pay close attention to the lengths and critical current densities metrics that are defined in the topic language. Of course, we're talking about phase 1, but looking forward, we would expect a phase 2 award to result in prototype lengths of magnet conductor, which could be tested in an R&D scale magnet. So bear that in mind as you enter into an application in this area. And research partners in this area are primarily the magnet design groups at the national labs. These include the group at Berkeley Lab, Fermi Lab, and Brookhaven. And again, if you have questions beyond this, Ken Markin is the primary PM for this topic. Both subtopics here, feel free to reach out to Ken via email. The second, cryogenic power electronics for distributed powering and quench protection of high temperature superconducting and hybrid magnets. Especially in this high temperature superconducting arena, we need improved diagnostics and observational tools for powered magnets that can provide observation for observing and optimizing magnet operation, particularly around quenching and training. As more and more sensors are included in the magnets, there is an increase in the number of power and instrumentation leads required between room temperature and the cryogenic environment. One method to manage the number of leads is to move more electronics inside the cryostat. And so having electronic systems that are compatible with that environment. There leads to a need for compact, efficient power amplifiers, current controllers, ADD converters, and other such electronic components that could be operable in the cryostat environment. And again, your primary R&D partners is the diagnostic group at Berkeley Lab. And again, Ken Markin is the PI. Advanced questions, reach out to him via email. But we'll take any immediate questions at this point.
Okay, there's one question for 26B.
Okay.
Would the power electronics be expected to perform in the 2 to 5K temperature range?
For HDS, we wouldn't be looking below 4. I think that's an open question, and yeah, so not super fluid type temperatures. Just what it would have to go down to, I think, is a kind of an open question for discussion, and one that I think you really would want to talk to Ken, and or if you know the folks in the magnetic design group at Berkeley, they would also be a great resource to chat with about this.
Thank you. Let me see. I don't see any more questions.
Okay, so we can pass off the hot seat. And again, by all means, the PMs are listed in the solicitation. Don't hesitate to email them. They'd be very happy to engage you.
Thank you for your time, Greg. Thank you for covering and
You're
asking
welcome.
questions. Thank you. Helmut, topic 27. Are you online?
Yes, I am. Can you hear me?
Yes, go ahead.
All right. So in this topic also has multiple subtopics. Subtopic A, radiation hard sensors and engineered substrates for detectors at high energy colliders. So here we're looking for sensors typically applied in our tracking and vertexing applications. We're looking for CMOS or CMOS-like processes that allows us to produce these sensors in a cost-effective way, because in these applications, we have to cover very large areas. Very large here means many, many square meters, up to 100 square meter. Typically, this is currently done in silicon, but we're also interested in other materials, preferably wide bandgap materials like silicon carbide. Another requirement we have is that these sensors need to be radiation hard, where the radiation doses they see is a strong function of distance to the beam and can reach very high into the hundreds of megarats. Subtopic B, novel interconnect techniques and integration. So in these collider applications, we very often have very high channel counts. So we need to have efficient interconnects down to very small pitches, 10 to 20 micron pitch. And we need to be able to integrate as much of the front-end electronics with the sensors as possible. So we're looking at 3D integration to the largest extent possible. Finally, subtopic C, electronics and sensors at ultra-low temperature experiments. So these are experiments operating in the deep cryogenic regime, that is 4 Kelvin and below. And we're looking to basically have computer-like power at the very front end in the 4K regime. So we're looking to build up logic structures and hold on a second, lost my train of thought here. Building up basically functional circuits and systems to have processing power available in the deep cryo regime. We're also looking for low noise amplifiers that work in this regime, like HEMTs or squids or parametric amplifiers. Often we also have the issue here of having a large number of interconnects that need to be superconducting. We need to have feed-throughs that connect the below 4K regime to higher temperature regimes where we have more electronics. And we're looking for all kinds of superconducting sensors of the type of transition edge sensors or kinetic inductance detectors or qubits and similar things. I think that's it for this topic.
Okay, there's a question for 27C. Are there specific detectors in specific labs which are being considered? Can we get names of people to contact for further specs?
Yes, I can give you contact information for our researchers working on specific topics there.
Okay, so the person should send you an email.
Yes, please.
Okay, for the person who asked about contact information, please contact Dr. Marceski. The email address is on the screen and it's also included in the topic document. The other question is, which national lab is relevant for 27C?
So there are multiple labs that are relevant here. I would again encourage you to contact me, and I can give you additional contact information for people at these labs.
Thank you. No more questions, so we'll move to the next topic. 28, and it's also yours. Go ahead.
Right, so again, we have multiple subtopics. First one, A, is low-cost, high-performance photodetectors. So here we're looking at a multitude of technologies to detect photons over a very wide wavelength range, going from the vacuum UV to the near IR. However, it is not typically the case that a single application needs to cover this full range. Rather, in a particular application, one is usually focused on a certain part of this wavelength range. So, for example, in our noble liquid detectors, we would be interested in having ways to detect UV, whereas in calorimetric applications that look at scintillating materials, we would be interested in photodetectors that look at say the visible range. Right, so no single detector needs to cover this whole range, but in all applications we have the requirement that we need to have very high efficiency. Often we need to be able to see single photons, often with very good time resolution, down to tens of picoseconds. And many applications also need to cover large areas with photodetectors, where larger means, again, multiple square meters or more. Right. Let's see. Subtopic B. So here we're looking for scintillating detector materials and wavelength shifters. This is typically for calorimetric applications in colliding beam or fixed target experiments. And our requirements are that we need bright, fast, radiation hard, and dense materials. And if you look in the text of the subtopic, there are some specs given what each of these requirements mean. We are looking for applications that realize this in the form of ceramics or glasses. We're not looking for scintillating crystals in this particular subtopic. And then last but not least, subtopic C, vibration-free cooling solutions for low temperature experiments. So we have a number of experiments that need to reach temperatures well below 1K, and that needs to carefully control vibrations, because that introduces noise into the measurement. So we're looking for new concepts for dry dilution refrigerators that operate continuously and operate virtually vibration free. That's it for this subtopic.
Okay, thank you so much. There is one question for 28B. Outside of high energy physics, how do you see these new materials being commercialized in other markets? Also, what are other markets that you would recommend developers considering?
So one obvious example here would be medical imaging. These applications typically seek the same kinds of requirements as we have in high energy physics, except for radiation hardness. And maybe their volumes are smaller than what we're looking at.
Okay, thank you very much. We're just gonna wait for a minute to see if there are other questions. Okay, I don't see any questions. Thank you for your time, Dr. Merceski.
Welcome.
Topic 29, Jeremy.
Hello, can you hear me?
Yes, go ahead.
Excellent. So this is topic 29, artificial intelligence and machine learning for high energy physics. It's a slight misnomer, as we are not actually seeking AI or machine learning models. We are seeking tools and sort of software tools that facilitate the training of AI ML models for HEP applications, and visualization tools to help understand those models and to help visualize scientific data that is produced. So as mentioned, the first topic is HEP AI ML training tools. And so what we are looking for are software libraries that can be interfaced with standard HEP analysis software. And there are several examples of these sorts of things. To do distributed training and to do distributed both as parallel training and data distribution on training on smaller subsets of data. And this comes from the fact that we have experiments with very large data sets, up to multi-petabyte scale data sets. However, when machine learning is trained, or when machine learning models are trained on this data, we often use just a fraction of that data. And so model or software libraries that can facilitate distributed training are sought, either through homogeneous computing systems, doing this simultaneously, or distributed across parallel computing platforms, and that train asynchronously. and also continuous learning, so tools that allow lifelong learning and not the hard-coded sort of training and inference phases, but libraries that allow us to sort of have models that evolve and grow over time as data conditions change. And so we seek these sorts of things that interface, as I said, with experimental collaborative software environments to allow more high-energy physicists to take advantage of these techniques.
Well, you can say
And that is topic A.
Okay.
I'm hearing someone else speaking.
Yes, just give me 1 second. I can mute. Go ahead.
Okay, so that's really the pitch for topic A. So if there are any questions, please let me know.
I don't see any questions.
Okay.
I think we can.
Yes. Oh, sorry. I did also want to include one other topic in this area are tools for physics-informed learning or tools that enable, the sort of physical understanding to influence the models that are developed. There is now a question.
Yes, it's for 29A. Would HPC resources be made available?
Yes, HPC resources can be made available if required. And if they are, we have supported SBIR companies to run specifically at NERSC on the Perlmutter HPC that they run there. So yes, so through the competitive ERCAP proposal, you can request time on NERSC and we will try and support it as appropriate.
Are you looking for a real-time system, meaning while tools are running?
Yes, so we seek applications that would do both. So continuous learning for real-time systems. These are sort of operations of HEP experiments or that process data while it's being collected to, sort of achieve a goal. That is one of the applications. However, non-real-time applications are also sought. So either is in scope.
Will HEP data sets be available for the purpose of testing?
That is sort of dependent on the data that is sought. So there are examples of open HEP data sets, not at the petabyte scale that I was referring at the beginning, but there are open data sets that can be made available and also partnerships with the DOE National Labs who are on HEP collaboration can be an effective way to gain access to these things depending on the collaboration and their rules around data sharing.
For real time, what is the data size per second rate?
That again greatly depends on whether you're targeting, sort of the Large Hadron Collider experiments where it can be up to terabytes per second, or whether you're looking at some of the other, experiments that can be much lower, but where you're looking to do, sort of anomaly detection. So they can be very high volume, but low rate, if that makes sense, in some of the liquid argon TPC experiments. So it depends on the application, but there's a pretty broad range.
Thank you. I don't see any more questions, so we can move to the next topic.
Okay, so topic 2 is in a similar vein. It is not for. Oh wait, sorry.
Sorry.
I didn't ask about the second.
I'm sorry.
No problem. So the second topic B here is the visualization tools, and so this is software to improve the visualization of scientific information that's natively integrated with both AI, and machine learning models and HEP software libraries, and so these should be able to generate scientific publication quality plots from machine learning models. So these would be things that make the interface to produce high quality publication results less cumbersome, to look more professional, to more natively support uncertainties and multiple types of uncertainties, asymmetric uncertainties, those sorts of things. And also to help visualize anomalous outcomes when compared to reference data. So looking at ways to analyze the data and what a machine learning model may be doing in a sort of a more intuitive manner that would allow you to gain some insight about the data set or what the model is doing. So basically to improve the visualization tools that we have for science and machine learning.
Okay. We're just gonna wait for a minute to give time to attendees to ask questions.
Mhm.
Okay, no more questions. So we can move to the next topic. Topic 30, and we have Michelle.
Hi, everyone. I was going to try to start my video, but I see I can't. So hi, everyone. Welcome. I'm Dr. Michelle Shin. I am the program manager for industrial concepts and what's called the technical topic manager for all of the topics. Can't do all this alone. I'm ably assisted. I have Dr. Gulshan Ray here. He's topic manager associate for the software. And I have also a Dr. Manasher Fakande, who is both a topic associate for the electronics. And he helped keep me out of jail. I don't want to get prison fit in a jail. And he's what we call the portfolio manager. And then I hope maybe that Dr. Elizabeth Bartosh might be able to join. But let me start out by saying a few things about NP. For successful, people want to know, well, how to get a successful proposal. Well, you have to understand that the requests in the subtopics come from the NP community, and they're really designed to be out there 5 to 7 years in the future. We can't take care of what they want right this instant. Phase 1 R&D needs to be coming in around TRL 3-4. That way you can ensure that you get a prototype done by the end of phase 2. We need that. It's a requirement in our topics, every one of them. You need to have a method or a prototype ready to go in a nuclear physics application or to be used in a nuclear physics facility by the end of phase 2. So you need to show that you've got very clear knowledge of prior art and as well as the state of the art in your topic area that you're applying for. And again, my subject matter experts, my colleagues and I, know that. So that's a very important, or you'll get rejected right at the letter of intent stage. Okay, so moving on, we move on to topic 30. This is nuclear physics software and data management. Gulshan, do you want to say anything, or do you want me just to sort of take it?
Michelle, why don't you take it? And if there are very specific questions, I can try to answer.
All right, very good. All right, so subtopic A is tools for large-scale nuclear physics data processing. So experiments at CBAF at Thomas Jefferson National Accelerator Facility, or currently RIC, which is still running for another year or so, at Brookhaven National Lab, produce 50 to 100 petabytes of raw data and for single experiments. In the future, we expect the facility at rare isotope beams and the future electron ion collider that's being constructed now at Brookhaven will have similar amounts. Now, we don't expect you to do any hardware. This is all going to be software development. And we don't expect you to figure out new ways to get the data from A to B because we have ESNet, which is quite a nice system. But the packaging of that data to try to do a reduced data set more efficiently and more easily perhaps than what can be done with the current software, which is usually something called root, is of great interest. We also, as you might guess, application to emerging data science. We really would like to see those emerging data science techniques applied in nuclear physics data. Now, this is This could be, in this case, it's really more set for these large experimental data sets. And you can possibly, we talk about artificial intelligence and machine learning, being able to help foster that, help move that forward, possibly doing some filtering type algorithm. However, I would be very careful that you don't make that, you know, the big tout of, well, we have this AI technique that works well on something that's not nuclear physics or high energy physics, something that's not in that data space. And because my reviewers will say, well, we're already doing that. And if we're already doing it, we're not interested in funding it. So be very careful on that. And in all cases, very important that you communicate and you say, here is how I am going to use this data technique for this particular community. And the communities we talk about are, say, heavy ions or medium energy, fundamental symmetries, theory, to name a few. They're all listed. I have created references, fresh references to all of our different communities. And then you can, of course, contact myself or Gulshan for some contacts, but it's a must. What we find otherwise is that you'll produce something and it doesn't connect to any particular community, and so no community wants it, and thus it just lies fallow, and we don't want that. On the heterogeneous concurrent computing, well, concurrent computing or heterogeneous is we have a combination of CPUs and GPUs. And so we are looking for better utilization of our high performance computing systems that Oscar runs, and you've heard about them in the leadership class facilities. And that supports both the theoretical and the experimental nuclear physics experiments. It could be a connection, I might again point out, say for medium energy, in which case, well, what experiment, what instrument, you know, getting data off. So for example, if you're doing nuclear structure, nuclear astrophysics, a new machine, a new instrument coming online very soon is Greta, which will be housed at EFRIB. So you would want to talk to the EFRIB or the Greta people and see what's out there that you could assist on. And that's it. We also, of course, have other. And Gulshan, do you want to say anything?
No, I think that's fine. I think we'll get questions and
I'm
we
sure.
can answer those specifically.
Very good.
There
All
is
right,
a question, Michelle, there is a question for subtopic C. Do you see the
Right.
question?
Yep. Heterogeneous concurrent or coprocessor hardware such as optimized on FPGA, GPUs sought, if coupled with the corresponding heterogeneous compute accelerator such as OpenCL. Ooh. I would think that would stay in C, don't you, Gulshan?
I think that should be, yeah, that would say that would be under C.
Yeah, we have to be careful because if they submit to the wrong one.
Mm-hmm.
And then the other thing, are there any needs for radiation hardened compute? And the answer is no.
Thank you.
Mm-hmm.
I'll click answered live. And I think we can move to the next topic.
Okay.
Topic 31, it's also yours.
All right, so topic 31. Before I start, I wanted to make sure, Monashare, do you want to say anything to this, or should I start and you be ready to answer any questions?
You're doing a wonderful job. At the end, I would like to just make a general comment about this topic, but go ahead.
All right, my friend. Thank you. Thank you, sir. All right, this is electronics design and fabrication. And essentially, what we're trying to do here is foster advancement in our detector instrumentation electronics, but we really do break it out away from instrumentation, although it is connected, tied in. So And so we refer back and forth between the two. So the first one, advances in digital processing microelectronics, is straightforward. We're looking at really at digitizers. So the digitizers sit away from the instrument. They're not in the radiation environment. Our next generation, what we're beginning to work on more, or what we're seeing the community want, are digitizers that could do either triggered, which is the old the conventional way, triggered at higher sampling resolution than what we normally, what we're even getting now. And so what we're looking at is effective number of bits needs to be 14. So then you've got bits on either side. So you really need a 16-bit digitizer at sampling rates greater than 4 gigahertz. And so, of course, your bandwidth needs to be high, 2 gigahertz. However, we would accept if you switch it into a streaming mode that you can drop the sampling rate. And so otherwise the data rate just comes flying out at such high rates that right now we don't really can handle it. Right now we're looking at a 16-channel minimum solution, but it must have a credible design for path to 64 channels. And any other specs are in the subtopic. Moving on, so that's our digitizers, but you've got to get data off the sensor, off the instrument. And so we have front-end application-specific ICs or ASICs. And generally, that is, of course, the first electronic component to process a signal from a detector element. And in many of these applications, at least some of them, they need to be radiation resistant. And the specs, again, are in the subtopic. They really are very close for the most part in terms of ADCs. Of course, we're mainly talking ADCs here, but it also could be TDCs. Thinking about ADCs, again, they need to be radiation resistant. That's in the topic, it's specified. And let's see, there was something else I wanted to say about that. There was, of course, that would be for something that runs at room temperature or close to it. We also have, and it's sort of interesting, the dovetailing with my friend Helmut and their subtopic on very low temperature. We also have superconducting detectors that we want to use in the EIC, a possible instrument that would go in one day in JLab called SOLID, and these would be superconducting. And so thus we need high channel count, 64 channels, in this case, superconducting ASICs that would be actually in the bath, so to speak. So if you're really low temperatures, less than 4 Kelvin, you cannot have something with 64 channels that's drawing, say, 5 milliwatts a channel. You're just going to overwhelm the chiller. So requirements include ultra low power, which is less than a milliwatt, and a high analog bandwidth greater than a gigahertz for these microelectronics. Hey, there we go. Monisher, do you have any comments?
Yeah, so thank you, Michelle. So Michelle works really hard communicating with the MP community every year to get more specifications. As you know, of course, electronics, you're not inventing anything new, but just simply pushing the edge, pushing the technology in terms of number of channels, number of bits, and also same thing on ACES, and essentially to get something that is more advanced, incremental improvements. So when possible, when we get the input from our community, we put those specs there, but they may not have every spec there. Some of them are just common sense. Some of them are just essentially, basically if it's so. And we often get before they have the LOI, we get often a lot of questions about specifications, and we can connect people to individuals, scientists, engineers in our field. But I think if it's not there, so that is something that you just have to think about or essentially research it yourself. And we obviously are very encouraging people to apply, to submit LOIs and applications, but please just, you've had in the past, and I don't want to sound negative, that people just simply take those specifications, say we shall provide, these instruments with so many number of channels, so such and such. So when you see those, when you see those specs, those really have really real meanings, and you should really have a feel for it. You should have understanding of it before you actually say, well, we'll provide such a device. Anyway, didn't want to be discouraging, but just I want to make sure that you understand those specs which are there for a reason, and if they're not there, there's also for a reason. That's all I have, Michelle.
Thank you, my friend. Another thing really fast is that folks normally like to write us and say, gee, we'd like to have a short meeting with you. And that always would be nice to have, but the reality of the situation is that we're so busy. And so what we like to do instead is we like to do first email communication. And actually we usually can get it all resolved by email. So we'd like to have the fastest way is to ask specific questions. Like I've got a whole set of questions here that it would be better to answer in email than it would be, in this meeting, but we can touch on that. Okay. So do you want me to end on the Q&A?
Yes,
want me to say a
go ahead,
few words?
Michelle.
Okay, so our guest here is asking, what's the expected magnetic flux density at the location of the superconducting front-end ASIC? Well, so we know that the SN SPDs, are going to sit at around 1.5 Tesla. It's not, and we know they can handle it. It's not. We have to be rather careful because, of course, if you raise the magnetic field too high, that you quit superconducting. So I don't have an exact information. That's not in the topic, so you'll need to email me on that. The expected number of events, of course, is going to depend on the application. If it's a very rare event detector, there won't be any, and there might be, one. But if it's on the other hand, an SN SPD sitting there near to the beamline of the EIC, it's going to be quite high. But I don't have that number in front of me. And so if you'll send me an email, you've got my email address, Ellie, I'll be happy to answer. Thank you. Okay, anything else?
There's
For
another
subtopic B, what is the expected result at the end of phase 1 and phase 2? All right, that's a great one. Well, it used to be that we would actually get a tape out, of an ASIC, depending on which one you're particularly interested in, whether you want, 31B1 or 31B2. That's getting harder, actually pretty much impossible when you're going down below, say, maybe at 130 nanometer node, you can do it, but not at 28 and below. But you need to have, you need to have a full design with a tape out, and with a cadence run. It would be very nice. You're going to have to do a really careful job of documenting that you can get down to the very low power draws. That's going to be key if you want to do the superconducting. If you want to do the other one, well, we're not particularly happy when you are like up around 25 milliwatts per channel. We'd like to see it lower, but that'll be a little bit TBD. Let's see, what else can I answer on that?
I think at the end of the phase
the phase 2. The phase 2, it's very clearly written at the end of every subtopic, and that is you need to have a full prototype. And typically people are usually getting that first ASIC tape out and testing it in the first year of phase 2, but it's got to be ready to go. You will have been able to have tested it as best as you can in your own facility, but usually by the end of phase 2, we see that getting out and being, you know, with an eval board or whatever, and getting tested by people in the community. Let's see. Is the superconducting front-end ASIC expected to be radiation hardened? Well, it depends. If it's, the superconducting one. The superconducting again, if we're talking about it being in the EIC, yeah, actually it does. Because you'll be right in really close to what happens in the EIC is that you've got light electrons colliding with hadrons, and so you get a big scatter for one and not for the other. So they're going to be really close in. So yeah, there's probably, in the case of the superconducting, if you want to go with an SN-SPD connected to it. If you wanted to do this for fundamental symmetries, on the other hand, no. We want the radiation environment to be as quiet as it can be. So you'll have to let us know what you're interested in. Anonymous attendee. That would be yes. Zena is typing that because that's not an answer. Short answers, I'm sure there is, but she will let you know. Okay, I think I've answered everything. Zena, are you back with me?
Yes, thank you so much. We'll move to the next topic, topic 32. Go
Awesome.
ahead.
All right, thank you. Okay, nuclear physics accelerator technology. So this has evolved some. In particular, in our subtopics, and we've reduced them a little bit. In the subtopics here, in materials and components for accelerators at NP facilities, these are essentially all superconducting. Although when you have superconducting assemblies called cryomodules, at the end of each one, of course, you've got gate valves and things like that. And of course, we want to be able to reduce particulate in there. And there's some discussion about that. But given that particulates invariably over time are generated and have a way of migrating where you don't want them, which is into the superconducting cavities, the usual way, if it's a particulate, it's very hard to remove without actually pulling the entire cryomodule out and disassembling it. We're still very interested in wondering if there's some way that you could create an in situ technique for removing particulates from the inner surfaces of those cavities. That's a hard ask, but that's there, because this is the kind of thing that would really save a lot of money across all facilities, and not just nuclear physics, but with our friends over in HEP and around the world. One new one that we're really I'm excited about was a suggestion that there be some automation of the assembly of these cavities. So you don't just have usually one big cavity or one cavity doing it all. You have a string. In the case of cryomodules at Thomas Jefferson, at Jefferson Lab, what you've got are you have a string of 8 of them. And these are all mechanically put together by hand in a class 10 clean room. We'd like to see if there's some automation aspect that could be demonstrated, could be created and shown, that would allow a completely autonomous assembly, you know, where human beings with all of our skin cells that shed and things like that are totally out of the room, and it basically puts this together, you know, puts the bolts in if there are bolts, tightens everything down, again, keeping everything super clean. So I'm pretty excited about that idea. In the RF and for RF beam acceleration systems, design and operations, we're looking not for a control system, but instead a hardware solution, which would allow the synchronization of multiple crab cavities. And there, we're looking at the systems that are being designed and built for the EIC. They're still interested in this, and there are specs on what we're looking for. And so that's primarily electron ion collider. There's also an interest still within primarily FREB, but it could be also used elsewhere. Control of being able to tune over a somewhat wider bandwidth than what you could do from any, say, RF source. Being able to control heavy ion, the resonators that are being used for heavy ion accelerators. In polarized beam sources and polarimeters, you'll notice that we're very interested still in ion sources that are longer lived, in particular for something like uranium, where the oven gets, has to get quite hot and tends to eventually fail. We're looking for something there. We are very interested in techniques to measure the degree of polarization non-invasively and we have specs from the community on what the energy range is and how carefully we need that measured. We really care a lot about rare isotope beam production. This is needed at both the FREB, but of course we also care about it eventually more for EIC, although those are pretty more standard. There are things like if you've got something like FREB, which eventually will be putting out a 400 kilowatt beam power, they're looking for higher emissivity targets. So obviously, even if you have water cooling, this thing's going to get hot and start to try to radiate. And if you have a higher emissivity in that mid-IR, then it's better to be able to get that heat out that way too. And again, all the specs are there. Really, really important, both in rare isotopes and in accelerate. There's some diagnostics that fall in, with the exception perhaps of our Atlas facility at Argonne. All of our machines are running really high powers. And so we're really looking for non-invasive diagnostics for optimum performance. And then we have other. Oh, let's see, I've got some Q&A. Those are both old. Nothing yet.
Okay, we're just gonna wait and see if there are questions. Just give attendees a minute to submit their questions. Okay. I guess we'll move to the next topic.
Okay, last one, 33.
Go ahead.
All righty. So we've after some thinking, we've reduced this. We've actually consolidated our subtopics. It used to be that we did for our first one advances in detector and spectrometer technology, but spectrometers are complicated, large instruments, and really you could do components within it, but in reality, it's really the detectors that go on a spectrometer, for example. That was what we care, or a calorimeter, for example. So there, what we're looking at there's an entire list, large area, lower cost, again, for detecting, analyzing, and tracking photons and charged and neutral particles. In many of these instruments, they're going to be placed in areas where the radiation field is high, and also they will be in the vicinity or within a magnetic field. The specs in those cases are given. What's the neutron flux anticipated? What's the gamma flux? Or probably the better way to say it is, what is the ionizing flux or dose? And then what is the magnetic field spec? So you can go look at that. The next thing is that we have rare decay or rare particle detection. So rare decay, you might think the two are really always the same, but not necessarily. In the case of rare decay, if we've got, say, at the facility for rare isotope beams, FREB, you could have something where you have created a species which has many, many more neutrons than what norm, and that's the whole idea of FRIB. And so then what the nucleus is stable. So it will spew out these, but because they're so rare that you can get that far out, it's a rare decay. And so this can be a rare, very weak or a very rare event, and we've listed that. Rare particle detection, we're doing fundamental symmetries, and in fundamental symmetries, we're interested in the possibility of a phenomena or a decay scheme, which is called neutrinoless double beta decay. And so there's a set of specs and some interest in there, and what we would need in there. You know, in all the cases with neutrinoless double beta decay or these rare events, you've got to avoid extraneous radiation. So for example, oh, I'm going to build this sensor. Well, if that sensor is made with silicon, well, guess what? Some of the silicon that you naturally get is going to have the isotopes which decay. So you've got to think about what you're going to do and how you're going to make things. Probably a simpler case that doesn't involve silicon is there's still a great need for cabling. I mentioned cabling, but really it's connectors. And so each of the different fundamental symmetries experiments has its own sort of style connector. So trying to make those radio pure would be of great interest and great importance. And again, we can start to get into specifics as we need to. And then we have other, and I don't know, oh, I think I have Elizabeth. If there's any questions I can't answer, she's not joined us. All right, for 33B, are there particularly labs or particular research groups that can provide specifications? And the answer, Alan, is absolutely. And send me an email and I can put you in contact with them.
Thank you.
Uh-huh.
Let's see. Oh, let's wait another minute to see if we are going to get more questions. Otherwise, we'll end the webinar.
Sounds good.
Okay, I thank you, Michelle. I don't see any questions. Thank you very much.
Thank you.
Thank you. And as we mentioned at the beginning of the webinar, we will post the slides along with the recording of the webinar on SBIR website under Funding Opportunities webpage. And here we have SBIR STTR Program Office contact information. Please feel free to contact us with any questions you may have. That will do for today's webinar, and thank you for attending.
Cool. Thanks, everyone.
Thank you.
Bye.
Bye-bye.
Bye-bye. See you, Hal.